The universe is trying to tell us something, and we have no idea what it's saying. Here's what we do know. The universe exists. It has rules. Physics works the same on Earth as it does in a galaxy 12 billion light-years away. The same equations that describe a falling apple describe the collapse of a star. That kind of consistency should make us feel like we understand something, like we've got a handle on reality. But there is one number, one single number sitting at the heart of everything. And that number is so wrong, so catastrophically, impossibly wrong, that physicists have called it the worst prediction in the history of science. Not a little wrong. Not rounding error wrong. Off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. And the terrifying part? That number is the reason you exist. The reason anything exists. And nobody knows why. Let's talk about the vacuum. Not the vacuum of outer space, though we'll get there. The quantum vacuum. The invisible fabric underneath all physical reality. According to quantum mechanics, empty space is not actually empty. It seethes. It boils. At the smallest scales imaginable, particles and antiparticles flicker in and out of existence constantly, borrowing energy from nothing and returning it almost instantly. These are called vacuum fluctuations, and they're not theoretical. They've been measured. They cause real, observable effects. The Casimir effect, where two metal plates placed nanometers apart in a vacuum are pushed together by the pressure of the quantum froth between them, proves these fluctuations are physically real. So empty space has energy. Physicists call it vacuum energy. And when they calculated how much energy the quantum vacuum should contain, they got an answer. A precise theoretical answer derived from the best physics humanity has ever developed. Then they measured the actual energy density of empty space. The two numbers didn't match. They didn't match in the way that a grain of sand doesn't match the observable universe. This is the cosmological constant problem, and it is, without exaggeration, the deepest unsolved mystery in all of science. Not just physics, all of science. It sits at the collision point between the two most successful theories humanity has ever built, and it reveals that something is profoundly, fundamentally wrong with our understanding of reality. To understand why this matters so much, we need to go back. Not just to the beginning of the universe, to the beginning of an idea. For most of human history, the universe was assumed to be static, eternal. Even Einstein, when he wrote his field equations of general relativity in 1915, found that his equations kept insisting the universe should be expanding or contracting. It couldn't sit still. But the prevailing assumption of the time was that the cosmos was steady, so Einstein did something that would later haunt him. He added a fudge factor, a mathematical term that acted like a kind of cosmic pressure pushing outward, balancing gravity, keeping the universe perfectly still. He called it the cosmological constant. He gave it the symbol lambda. Then Edwin Hubble looked through his telescope. In 1929, Hubble confirmed what had been slowly becoming impossible to ignore. Galaxies were moving away from us. All of them. And the farther away they were, the faster they were receding. The universe wasn't static at all. It was expanding. Had been since the very beginning. Einstein abandoned his cosmological constant immediately. He reportedly called it the greatest blunder of his life. Lambda was erased from the equations. And then, 70 years later, it came roaring back. In 1998, two independent teams of astronomers were doing something seemingly routine. They were measuring the distances to a specific type of exploding star called a Type Ia supernova. These supernovae are extraordinarily useful because they all explode with roughly the same intrinsic brightness. They're cosmic yardsticks. By comparing how bright they appear to how bright they actually are, you can calculate exactly how far away they are. And by measuring how fast they're moving away from us, you can trace the expansion history of the universe. The teams expected to find that the expansion was slowing down. That made sense. Gravity is attractive. All that matter pulling on all other matter should be putting the brakes on the universe's growth over time. What they found instead stopped the physics community cold. The expansion wasn't slowing. It was accelerating. The universe was flying apart faster and faster. Something was pushing space itself outward, overwhelming gravity on cosmic scales. Something invisible, something that filled all of space uniformly, something with a negative pressure that acted like anti-gravity. They called it dark energy, and when they measured how much of it there was, the value matched Einstein's discarded cosmological constant almost exactly. Einstein's greatest blunder turned out to be right for entirely the wrong reasons. Now the question became what dark energy actually is. And the most natural candidate, the one that quantum mechanics had essentially predicted was there all along, was vacuum energy. The energy of empty space. If the quantum vacuum really does contain energy, and we know it does, then that energy would have exactly the properties dark energy seems to have. It would permeate all of space uniformly. It would exert a kind of outward pressure. It would cause accelerating expansion. So physicists did the calculation. They took the best equations from quantum field theory and calculated what the vacuum energy density should be. The answer was 10 to the power of 120 times larger than what we observe. Let that sit for a moment. If the vacuum energy were as large as quantum mechanics predicts it should be, the universe would have been ripped apart in the first fractions of a second after the Big Bang. There would be no atoms, no stars, no galaxies, no planets, no biology, no time to develop consciousness to even notice that nothing exists. The cosmos would have detonated into a sea of pure energy and then vanished. But it didn't. And the reason it didn't seems to be that the vacuum energy is almost exactly zero. Not quite zero, because that tiny non-zero value is what's driving the accelerating expansion we observe. But it's so close to zero that it requires an almost perfect cancellation of some kind, where some positive contribution is cancelled by some negative contribution to leave this vanishingly small remainder. The problem is that nobody knows what mechanism could produce that cancellation. There's no known physical process that would naturally balance the equation to exactly the right value. The observed value of the cosmological constant is not predicted by any theory. It just is. And its existence at exactly the value needed to allow the universe to expand gently enough for galaxies and stars and planets and life to form is one of the most unsettling coincidences in all of physics. Some physicists think it isn't a coincidence at all. That's where the multiverse comes in. The anthropic principle is an idea both simple and deeply controversial. It says that the reason we observe a universe compatible with life is because only a universe compatible with life can produce observers. If the cosmological constant were slightly larger, the universe would have expanded too fast for gravity to gather gas into stars. If it were slightly smaller, everything would have collapsed back in on itself billions of years ago. The fact that we exist at all selects for a universe with just the right value. Some physicists, particularly those working on string theory, have proposed that the cosmological constant isn't a fixed number but a variable. That the fundamental equations of physics allow for an enormous number of different possible universes, each with different values of lambda, different laws of physics, different particle masses. A vast cosmic landscape of possibilities. Most of these universes would be dead. Their constants would be incompatible with complexity. But somewhere in that landscape, by sheer statistical weight, some universes would have lambda near zero. And those are the ones that produce observers. We live in one of them not because it was designed or because some deep physical law requires it, but because it's the only kind of universe we could find ourselves in. This is called the landscape multiverse, and it makes a lot of physicists profoundly uncomfortable. Because if it's true, if there really are a vast or infinite number of universes with different physical laws, and our universe's properties are explained purely by the fact that we exist to observe them, then the cosmological constant problem doesn't have a deeper explanation. There's no equation to derive it from, no mechanism to discover. Physics becomes fundamentally unable to predict the most important number in the universe. And that feels less like a solution and more like a surrender. Others refuse to accept that. They believe there is a mechanism, something we're missing. Some principle of physics not yet discovered that would make the near-zero value of the cosmological constant inevitable rather than accidental. These physicists are hunting for what they call a technical solution. A symmetry, a new field, a new particle, something that would naturally cancel the vacuum energy contributions to leave exactly the tiny observed value. Supersymmetry was one of the great hopes. It proposed that every known particle has a partner particle with complementary properties. Bosons paired with fermions. The vacuum energy contributions of one type of particle would cancel the contributions of the other. Mathematically elegant. Physically satisfying. But the Large Hadron Collider at CERN, which smashed protons together at energies never before achieved in a laboratory, should have found evidence of supersymmetric particles by now. It hasn't. Not a single one. Supersymmetry isn't dead, but it's wounded. Other proposals involve so-called quintessence, the idea that dark energy isn't a true constant at all but a dynamic field that changes slowly over time. If quintessence is real, then the expansion of the universe hasn't been accelerating at a fixed rate. It should have varied. And if we can measure that variation precisely enough, we can map the behavior of dark energy over cosmic time. The Dark Energy Spectroscopic Instrument, known as DESI, began collecting data in 2021. In 2024, its first results suggested that dark energy may not be constant, that it may be evolving. The signal is tantalizing but not yet definitive. If confirmed, it would overturn decades of cosmological assumptions and open entirely new theoretical terrain. But let's widen the lens even further. Because the cosmological constant problem, as profound as it is only one face of a deeper mystery. Dark energy is one of the two great invisible forces shaping the universe. The other is dark matter. And together, these two unknowns account for 95% of everything that exists. Read that again. 95% of the universe is made of things we cannot see, cannot touch, and do not fundamentally understand. Everything you've ever looked at, every star in the night sky, every planet, every galaxy, every atom in your body, all of it adds up to less than 5% of the total content of the cosmos. We know dark matter exists because we can see what it does. Galaxies rotate in ways that don't make sense unless there's a lot more mass present than we can account for. Fritz Zwicky noticed this in the 1930s when he measured galaxy clusters moving faster than their visible mass should allow. Vera Rubin confirmed it in the 1970s with painstaking measurements of galactic rotation curves. Galaxies spin too fast at their edges. Stars at the outer rim of a galaxy move as fast as stars near the center. That shouldn't happen. Without dark matter, those outer stars should fly off into intergalactic space. The fact that they don't mean something is holding them in. Something massive. Something invisible. We can map where dark matter is. Gravitational lensing, the bending of light around massive objects predicted by general relativity, lets us trace the distribution of dark matter through the way it warps the images of background galaxies. The Bullet Cluster is perhaps the most beautiful piece of evidence. Two galaxy clusters that collided, their hot gas slammed together and slowed down by electromagnetic forces, but their dark matter halos pass straight through each other like ghosts, because dark matter doesn't interact electromagnetically at all. We watched the collision and saw the matter separate from the mass. That image is as close to direct evidence of dark matter as anything we have. But what dark matter actually is remains unknown. The leading candidates have shifted over the decades. WIMPs, weakly interacting massive particles, were once the dominant hypothesis. They fit beautifully into theoretical models of particle physics. But experiment after experiment has failed to detect them. Underground detectors the size of houses filled with liquid xenon, instruments so sensitive they can detect a single photon, have searched for years and found nothing. Axions, primordial black holes, sterile neutrinos, each candidate has its advocates and its problems. The irony is almost cruel. We can measure dark matter's effects with extraordinary precision. We can create maps of its large-scale structure across the observable universe. The cosmic web, that vast invisible scaffolding of dark matter filaments along which galaxies form and cluster, has been reconstructed from surveys of millions of galaxies. We understand, in broad strokes, how dark matter shaped the universe from the first moments after the Big Bang to the present. And yet we cannot say what it is made of. We cannot point to a single confirmed dark matter particle. And here is where the mystery deepens in a way that feels almost philosophical. We have two unknown things: dark matter, which seems to cluster and clump and behave almost like ordinary matter but without electromagnetic interactions, and dark energy, which fills space uniformly, doesn't cluster at all, and drives everything apart. They seem completely unrelated, different in every way. And yet they both have to exist at exactly the right quantities for our universe to look the way it does. The density of dark matter is just right to have seeded the large-scale structure of the cosmic web. The density of dark energy is just right to have begun accelerating the expansion at roughly the era when complex structures like galaxies had already formed. If the acceleration had started earlier, it would have prevented galaxies from forming at all. If it started later, it might never have begun. These two invisible quantities seem almost coordinated, and we have no idea why. There are alternative ideas. Modified gravity theories, like MOND or its relativistic extensions, propose that we don't need dark matter at all. That gravity itself behaves differently at low accelerations than our current equations predict. Some of these theories have had surprising successes predicting the properties of specific galaxies. But they struggle to explain the large-scale structure of the universe, the bullet cluster, the cosmic microwave background. They haven't replaced dark matter so much as complicated the picture further. And then there's what some physicists call the crisis in cosmology. For decades, the standard model of cosmology, lambda CDM, standing for lambda cold dark matter, has been astonishingly successful. It predicted the pattern of temperature fluctuations in the cosmic microwave background, the ancient afterglow of the Big Bang. It predicted how galaxies would cluster on large scales. It matched observation after observation with stunning accuracy. It seemed like the framework was essentially complete. But in the last decade, cracks have appeared. Not small cracks. Deep, structural ones. The most troubling is called the Hubble tension. The Hubble constant is the rate at which the universe is currently expanding. You can measure it two very different ways. One method looks at the cosmic microwave background, the patterns of the early universe, and extrapolates forward using the standard cosmological model. The other method measures the distances and recession velocities of nearby galaxies directly, using those type Ia supernovae and other distance indicators. Both methods are extraordinarily precise. Both have been repeated and refined by independent teams using independent instruments. They disagree, by enough that it almost certainly isn't a measurement error. The early universe measurement gives a Hubble constant of around 67 kilometers per second per megaparsec. The late universe measurement gives about 73. That gap, roughly 8%, has grown more statistically significant with every improvement in measurement technique. Astrophysicists speak of it now at 5 sigma confidence. In physics, 5 sigma is the threshold for calling something a discovery. The Hubble tension is real, and the standard model cannot explain it. If the tension is real, it means one of two things. Either there is a systematic error lurking somewhere in the observations that nobody has yet identified, or the standard cosmological model is missing something. Some physics that operated in the early universe that we don't know about. An early dark energy component. A new particle. A new interaction. Something that changed the expansion rate in the first moments after the Big Bang and left a permanent imprint that our late universe measurements pick up but our early universe extrapolations don't account for. The James Webb Space Telescope has been looking into this. Its extraordinary resolution and infrared sensitivity allow it to measure stellar distances with unprecedented precision. Its early results haven't resolved the tension. If anything, they've sharpened it. The disagreement stubbornly persists. And so here we are, standing at the edge of what we know, which turns out to be a much closer edge than we thought. We have a universe whose expansion is driven by something that fills empty space with energy we cannot explain at a value that should be impossible. We have a universe whose structure is scaffolded by invisible matter we cannot identify despite decades of searching. We have two competing measurements of how fast the universe is growing that refuse to agree. We have equations that work extraordinarily well in certain domains and catastrophically fail to reconcile with each other in others. General relativity governs the very large. Quantum mechanics governs the very small. Both are the most precisely tested theories in the history of science. And they are fundamentally, mathematically incompatible. A complete theory of quantum gravity, a framework that unifies them, remains out of reach. String theory is the most developed attempt, and after decades of theoretical work involving some of the most brilliant minds in physics, it has yet to make a single testable prediction that distinguishes it from alternatives. There is a humbling paradox at the center of modern science. The better our instruments become, the more clearly we see how much we don't understand. The Hubble Space Telescope gave us depth. Webb gives us more depth. And each new image doesn't solve the mystery. It multiplies it. Every galaxy we see is embedded in a halo of dark matter we can't see. Every point of empty space between them seethes with vacuum energy we can't explain. Every photon that reaches our telescope has traveled across a universe that is flying apart, accelerating into a future that may be unreachable. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. That will be spectacular, a slow-motion cosmic collision that takes hundreds of millions of years to resolve, two swirling islands of stars passing through each other, their dark matter halos merging, new stars igniting from compressed gas clouds. Life, if it still exists anywhere, will have a front-row seat to a display that dwarfs anything in current human experience. But much further in the future, if dark energy continues to accelerate the expansion, something strange happens. Galaxies that are currently visible to us will accelerate beyond the cosmic horizon. The light they emit will never reach us. Not because it's too faint, but because space will be expanding faster than light can cross it. Over trillions of years, the universe as seen from any given point will grow increasingly dark. Galaxies will vanish from view one by one, not through death but through distance. A civilization living a trillion years from now, if one could exist, would look out into an almost empty sky and have almost no evidence that other galaxies exist. The cosmos would appear to consist of a single island of stars surrounded by infinite darkness. They might conclude, with all their science and all their instruments, that the universe is just one galaxy. And they would be as wrong about the universe as we might be about something even more fundamental. That thought should unsettle us. Not in a paralyzing way, but in the most productive way possible. Because it means we are living in a cosmically privileged moment. Right now, we have enough light to piece together the history of the universe. We can see the cosmic microwave background, the afterglow of the Big Bang. We can trace the distribution of galaxies across billions of light years. We have clues, billions of them, streaming toward us every second. But those clues are temporary. The universe is slowly erasing its own history. The greatest unsolved mystery in the universe might not just be a puzzle waiting for the right equation. It might be an invitation to look harder, think deeper, question more radically. The cosmological constant problem isn't just a number that doesn't add up. It's a sign that our theories, however precise, are incomplete. That physics as we know it is a map, and maps are never the territory. Vera Rubin, whose patient observations revealed the invisible mass holding galaxies together, said something worth remembering. She said that in a spiral galaxy, the ratio of dark to luminous matter is about a factor of 10. That's probably a good approximation to the ratio of our ignorance to our knowledge. That was decades ago. We've learned an enormous amount since. And the ratio of our ignorance to our knowledge has somehow grown larger. There's something almost beautiful about that. Not comforting exactly, but beautiful in the way that standing on a cliff edge is beautiful, with the full depth of an ocean below you and a horizon so far away it curves with the earth. The mystery doesn't make the universe feel unknowable. It makes it feel alive. Like the cosmos is still unfolding, still revealing itself, waiting to see if the patterns it has spent 14 billion years composing will eventually find a mind capable of reading them. We built instruments that can detect the stretching of space-time by a fraction of a proton's width. We decoded the ancient light of the first atoms. We mapped the universe's invisible skeleton. We watched stars die in real time across distances that make the mind go quiet. And still, the vacuum hums with energy we cannot calculate. The dark matter moves silently through us, through this room, through you, right now, without leaving a trace. The universe expands into a future we cannot see, driven by a force we cannot name. The greatest unsolved mystery isn't a failure of science. It's science working exactly as it should, finding the edge of what is known and staring into what isn't, with instruments and equations and the strange human compulsion to understand things that don't have to be understood. The universe doesn't owe us an explanation. That we keep asking for one anyway is perhaps the most remarkable thing in it.